The real methods I want to talk about are density functional theory. In the 1980s, really, a pair of theorems was uncovered. They're really very simple. And what those theorems together say is that the exact solution of the Schrodinger equation is a function of the electron density. Now that's a very powerful statement because the electron density is something that is actually calculable rather easily. And it's saying that if I know the density precisely, it's also something that's measurable. This is what X-ray diffraction does. If I know the density and then I know this function of the density, then I can solve the Schrodinger equation rather trivially. This is Walter Kohn. He got a Nobel Prize with John Popel in the same year. Good sharing, actually. The huge advantage of density functional theory is that it is, in principle, very inexpensive. In principle, it will scale as third or the fourth power of the size, whereas these good wave function-based methods I was talking about will scale as the fifth, sixth, seventh, and higher powers. And so really, really very many orders of magnitude easier. The big disadvantage of density functional theory is that we don't really know what this function is, and there's no way of, at least there's no way discovered, of actually knowing how to improve. So once you have a given description, how do you make it better? With Hartree-Fock theory or with wave function-based theories, you actually know how to make it better. Here you don't. Now, the result of this is that people have played a great deal with different functionals, and I'm going to put that in a minute. But the first comment I want to make is that density functional theories are biased. They're parameterized. The theorist community doesn't like to admit this, but all these theories, as far back as one of the most popular functionals, this thing called B3LYP, which people who've done modeling will recognize that name, have parameters in them. And that means that you have to be careful of biasing your theory to get the results you want. That's something you have to really try to avoid. How do you choose a functional? This is probably the most intimidating part of sort of recent modeling experience, last 10, 20 years, in the sense that there are literally hundreds of choices. They all start with a single approximation, which is called the generalized gradient approximation. And what that says is that the function you're looking at is not only a function of the density, but it's a function of the density and the gradient of the density, the derivative of the density. So we're going to start there. There are earlier theories. They're really not worth anything at this stage. If I look at these, I'm going to list, I think, 8 functionals, just to intimidate you a little bit. The most commonly used one still, and it shouldn't be, is called B3LYP. It is what is called a global hybrid generalized gradient approximation. What it says is that we're going to mix in a piece of Hartree-Fock theory as a constant into this function. Okay, that's what global hybrid means. B3LYP, the common one, has 3 parameters. That's the 3 in there, and those parameters were selected almost haphazardly. It's amazingly successful given the case. More recent functionals have taken a different approach. They've said, let's develop a database of information, not primarily from experiment, although there is some experiment in there, but primarily from calculation. And let's develop that database mainly of reaction energies. There's some structures in there as well. And we're going to use that to parameterize these functions. Okay, so the big work was developing the database, and that's still ongoing. There are two groups that are heavily involved. There's the group of Chular at Minnesota and the group of Head Gordon at Berkeley. And there are other groups, I don't want to belittle them. The important ones here, there's a pair of them called, again, terrible names, Omega B97XD and XV. Those are called global range separated hybrid generalized grade, big names. What they mean is I'm going to mix in the Hartree-Fock in a way that is dependent upon the density. So the amount of mixture is actually dependent upon the density. So we're gonna go past B3LYP. Instead of putting Hartree-Fock theory as a constant, we're going to put it as a function of density. We're also going to add to the tail end a term which is going to account for long-range interactions, so-called dispersive interactions, things that hold molecules together in a liquid. And there are two ways of doing that. You can do it empirically, that is /D, or you can do it analytically. You can actually try calculating those long-range terms, which is rather costly. But they're similar in concept. A third functional is a very simple one. It's missing the Hartree-Fock term. But instead of that, it throws in the derivative of the kinetic energy, which is really the second derivative of the density. This is one due to Head Gordon, and it's called B97MV. Its principal advantage is that you don't have to calculate the Hartree-Fock component, which makes it significantly less expensive. Going further, this is a Chular functional. This one mixes in the Hartree-Fock theory as a constant and also allows for the derivative of the kinetic energy, or the second derivative of the density, same thing. I'm going through these rapidly to accomplish something. I really want to intimidate. I really want to show you that there's a morass of people's ideas out here. And at some point you have to settle and say, well, what am I going to do? Okay, let me go one more. Here's a recent development, and it's a development which I personally dislike. This says, let's take the best of the functionals that we've done, and we're going to add in a component which deals with exciting electrons from the ground state to the excited state. These are called double hybrid functionals. And the reason I don't like them is because the original theory says the solution of the Schrödinger equation depends on the density. The density has nothing to do with mixing in higher components due to higher orbital promotions. But these are becoming popular. This quote simplifies it. We start with one of two things. We either start with what's called the generalized gradient approximation, which says the fundamental component is the density plus the gradient, or we start with something which says the fundamental component is the density plus the gradient plus the second derivative. It's usually couched as not the second derivative, but the first derivative of the kinetic energy. It's very similar. We then say, what do you do with regard to Hartree-Fock theory? We don't include it. This is called the Hartree-Fock exchange. We include it as a fixed amount, or we include it as a variable amount, fixed and variable relating to the electron density. And then finally we say, what do we do with long-range interactions? We don't do anything. We put them in empirically, or we actually try to calculate them. And then finally, I guess you could stretch from any of these. The only one I'm going to talk about is you account for contributions due to electron promotion. So this is a way of diagrammatically putting something which is very complicated. If I'm understanding the question right, in the case of trying to look at things which are two molecules interacting, or the conformation of a molecule is the same thing, where you have some big molecule and two ends, or they're really two independent molecules at that point. Yes, these dispersion components are very important. Now, whether you can get away with it empirically or actually have to calculate it, that's a separate item. But the empirical ones are basically just doing a sort of just adding the van der Waals equation onto the thing. And that actually works pretty well. But you can actually calculate that or put in a guess at what that looks like in the functional. And that's quite costly, but it may be worthwhile.